What's up, guys? I just wanted to post a quick video on these questions from page 103 in your notebook on empirical and molecular formulas. I just made an entire video on it. As you can see, a lot of my work here, and even though the microphone was on, something happened. So I'm a little bit scared this video is not going to have sound either. I did a little test, but we'll see. Anyway, I worked through these, so if you want to pause the video and look at my work on this one, go for it. If you want to pause the video and look at my work on this one, go for it. But I'm pretty tired, and really this last question combines both of them. So I figured I can just go through this one step by step and break it up into the two separate parts as much as I can, and you'll be able to see the process either way. So let's jump in. Read it first. An unknown compound was found to have a percent composition as follows: 47.0% potassium, 14.5% carbon, and 38.5% oxygen. What is its empirical formula? And that's all we're going to focus on right now. So this first part of the video, this first thing I'm doing is just finding the empirical formula of this. I was given percent composition. Just like in this first question here, it's asking for empirical formula from the percent compositions of the atoms within it. Okay, that's all we're doing right now. So I already wrote out my elements and the percentages. Now the first step when finding an empirical formula is to divide the value of the percent by the atomic mass of the element you're looking at. So here I have a value of 47.0, and I'm going to divide that by the atomic mass of potassium, which is 39.10. Okay, and that's going to give me 1.20. All right, now I go on to carbon. So I'm going to divide 14.5 by 12.01, and that is going to give me a value of 1.21. All right, and then lastly I go on to oxygen, 38.5 divided by 15.99, and you might do 16.00, that's fine. Either way, you're going to get pretty much the same answer. It's going to give me 2.41. Okay, so now I have three numbers. A lot of people make the mistake of thinking this is where you stop, that those are going to be the subscripts in your formula. That is not the case. Okay, we just figured out the masses of each of these elements within the compound. Now we need to figure out the ratio to each other. Okay, so we figure out, and we're not just figuring out any ratio, we're figuring out the lowest whole number ratio. That's what an empirical formula is. So we're going to figure that out by dividing each one by the smallest number, because when you do that, you're going to make that smallest one 1, and you're going to get the ratio of the other ones to that. So we're going to divide by this 1.20 because that's the smallest number. Okay, so I'm dividing all three by the smallest number. That is going to give me, obviously, 1 for potassium. It is going to give me 1 also for carbon, slightly off from 1, but we're rounding to whole numbers here. These are subscripts. You can't have a partial element, so it's going to be a whole number. And then here, it's going to give me about 2. Okay, I don't have a half here. If I had a half, like let's say, for example, if it was 1.5 here somehow, then I would multiply everything by 2. And I would have 2, 3, 4 as my subscripts. But we don't have a half here, and we don't need to worry about that. Okay, so we just found our subscripts for this formula. So our formula is going to be as follows. The empirical formula will be potassium once, carbon once, and oxygen twice. Okay, so I took this 2 and I put it here. The other ones have 1s. So this is our empirical formula. All right, so that's the first part of this problem, is finding the empirical formula. That's what this first question was all about, finding the empirical formula. Now, we're given the molar mass of the compound we're looking at, and we're being asked for the molecular formula. So if you look at the second question, it starts by giving you the empirical formula of something, and then giving you the molar mass of that thing in the compound you're looking at. and ask for the molecular formula. So that's where we are right now. We found our empirical formula, and now we're given a mass, and we're asked to find the molecular formula. So whereas the empirical formula is the lowest whole number ratio of atoms in an element or in a compound, the molecular formula is like saying what is actually in front of me right now. All right, and this is very useful in a lab situation where you have to try and figure out if the compound you just made is the compound you were trying to make. You have to figure out the percentages, you have to figure out the masses, and you have to see if it's what you're looking for, and if not, what is it? So we have our empirical formula, as I just said, and we have a mass. So let's go down here, and we're going to put our empirical formula right here for reference. It is KCO2. Now our first step is to find the molar mass of our empirical formula. So we're going to add up the atomic masses. We have 1 potassium, and potassium weighs 39.10. We have 1 carbon, which weighs 12.01. And we have 2 oxygens, which each weigh 16.00. All right. So we're going to just calculate molar mass as we do. So this is going to be 32.00. The other ones are going to stay the same. So I'm going to get, I'm adding right now, I'm adding these all together. And I'm going to get 83.11. Okay, this is the molar mass of the empirical formula. Okay, that's what I'm looking at right here. Now up here I was given the molar mass of the molecular formula of the compound that I have. So the next question, or the thing we're trying to figure out now, is how many times does this empirical formula, the simplest whole number ratio of this compound, fit into the molecular formula that I actually have? How many times does this fit in? So we're going to do that by, we're going to take the molecular molar mass, and we're going to divide it by the empirical formula molar mass. Okay, because what is division? Division is telling me how many times this goes into this. How many times does that fit into that? That's what dividing tells us. So in our case, this is going to be 166.22 divided by, it's really ugly, divided by 83.11. Okay, so we're trying to figure out how many times does our empirical formula fit into our molecular formula, because the molecular formula is just the actual empirical formula. Is going to be greater than the empirical formula in most cases. Sometimes they're the same. But we're going to see that this 83.11 goes into 166.22 twice. So this is going to equal about 2. All right, so that's how many times the empirical formula fits into the molecular formula. That means that our empirical formula is going to be doubled, multiplied by 2. So we take 2 and we're going to multiply it through our empirical formula. All right, so we write out the empirical formula. We're going to multiply through. So that means that it's going to be 2 multiplied by the atoms in here, which is 2 multiplied by these subscripts. So we end up with, I'll write it over there, we end up with K2, C2, O4. This is our molecular formula. Okay, so we started out to find the empirical formula, taking the percentages, divided by atomic mass. You get your value, divide each number by the smallest number, and then you get your subscripts right here, and you apply them and get your empirical formula. Then you come down here, you get the mass of the empirical formula. You divide the mass of the molar mass of the molecular formula by the molar mass of the empirical formula. You get your amount of times your empirical formula fits in there, how many times it's going to be multiplied to get the molecular formula you have in front of you. So you multiply it through the empirical formula, and that will give you your final molecular formula. All right, I hope you guys found that helpful. If you were confused, I hope you attempted on your own first and you know this process well.